Reading log-scale graphs and why we use them, Part 2. In our first video, we talked about how log-scale graphs are useful. In this video, we will talk about how to interpret log-scale graphs. Interpreting steepness on linear-scale graphs. If we look at the steepness of a single linear-scale graph in two places, we can make general comparisons. This linear-scale graph tells us that South Korea's daily cases on December 1st was increasing faster than on June 1st. But we really need to look at the values on the axes to fully understand what the steepness of a linear-scale graph means. Look at these two linear-scale graphs of the exact same data. On January 1st, the steepness of the linear-scale graphs are different only because the vertical scales are different. But the daily cases for January 1st and 2nd and the slope formula from high school math class give us the same slope value on both linear scale graphs. The graphs look different because of different scales, but they show the same situation. South Korea's cases at the start of January were decreasing by 45 new cases per day, regardless of what graph or scale we are using. Interpreting steepness on log-scale graphs. The steepness of log-scale graphs doesn't have the same meaning as steepness of linear-scale graphs. On log-scale graphs, even when viewing one graph, it is even more important to look at the values on the axes. Whether we use a linear-scaled or log-scale graph, the number of daily new cases on January 1st and 2nd are the same. So at the beginning of January, the U.S.'s daily cases were increasing by over 11,000 new cases per day. Even though the graph looks steep on the linear scale and flat on the log scale, the slope is the same, over 11,000 cases per day, on both graphs. We shouldn't use steepness to judge whether a situation is getting better or worse on log-scale graphs. Because of how log-scale graphs are made, we shouldn't even compare steepness on two parts of the same graph. On March 2nd, 2020, the slope is 5 new cases per day. On January 1st, 2021, the slope is over 11,000 new cases per day. Daily cases were going much faster on January 1st, but the graph is steeper at March 2nd. So how should we read a log-scale graph? Seeing 10 times as much on log-scale graphs. On a linear-scale graph, we use equal spacing to add the same amount over and over on the vertical axis. But on a log-scale graph, we use equal spacing to multiply the same number over and over, in this case 10. This kind of graph can help us see how long it takes for daily cases to get 10 times as large. Let's look at the very beginning of the COVID pandemic in the US. Starting on January 26, 2020, for daily cases to go from 1 to 10 or get 10 times as big, it took 38 days. But for daily cases to get 10 times as big again, to 100 a day, it took only 6 more days. And for cases to get 10 times as big again, to 1,000 a day, it only took 8 more days. The situation was getting worse. Keep in mind, how long it takes to be 10 times as large doesn't always tell us whether a situation is getting better or worse. If daily cases are already really high, then a situation can be severe even if the time for daily cases to get 10 times as big is quite long. At the beginning of a pandemic or other exponentially growing situation, it's important to see how fast things are doubling or tripling or getting 10 times as big. Log-scale graphs are especially useful then. The big idea we must remember is, to interpret log-scale graphs, or indeed to interpret any graph, we must carefully look at the numbers on the axes and not the steepness of the graph.